All right, let's do a little bit of calculation here with our ideal gas law. So we've got a problem here. We see that we have 0.25 moles of a gas. Okay, so that lets us know. Oops. So this right here, that's our N. Okay, that's our N value. And then, of course, that right there, I mean, that's pretty easy to look at. That's the temperature. So the ideal gas law, remember we have PV equals nRT. So remember, R is our constant, right? R is our ideal gas law constant, right? So there's nothing in here that directly talks about the pressure itself. And so when something like that happens, what you can just naturally assume is that you can use the atmosphere. Excuse me. You can use atmospheres for the pressure, which is convenient because that's just the number one. That makes math really, really easy. All right. So let's list out what we've got here. We've got pressure equals 1 atmosphere. All right. V. It says temperature readings are this. What volume of space will the gas need to contain? All right, so we're solving for volume. Right, we need to know how much volume of space is there, the gas is going to take up. That's essentially what this question is asking. So there's the V. So N, well, we see up here that's 0.250 moles. We know what R is. R is 0.0821 atmosphere liters per mole Kelvin, right? And we know we're using mole Kelvin or atmospheres because remember, since there's nothing in the problem, we're just going to assume 1 atmosphere. And so this is the R value we use when we use atmospheres, right? It's a different R value if we use millimeters of mercury or kilopascals, right? And then temperature is 22.78 degrees Celsius, but we have to add 273 to that to turn this into Kelvin. So we've got 22.78 plus 273. That gives us 295.78. 295. Yep, 295.78 kelvins. We now have everything we need. Just simple plug and chug, right? Let's give ourselves a little bit of room to work with here. All right, so we're solving for V. This is what we're solving for right here, right? This is what we're solving for. So we need to isolate that variable right there. So obviously we would divide this side by P. So we would divide this side by P as well, right? And so now that gives, and then so obviously it crosses out here, right? So that gives us that volume is going to be equal to nRT divided by P. And these are all capital letters, except for the N, right? These are all capital letters. So that's it. It's pretty easy. This is just basic plug and chug. The hard part, not the hard part, but the challenging part I've seen for students is if you're used to just punching numbers into a calculator and you always worry about should I multiply or divide. You don't ever ask me or anyone else, do I multiply or divide these? If you rearrange the equation tells you if you multiply or divide. This equation says multiply those three together and divide it by that. All right. The difficulty I see is people having trouble processing the equation with the units, and so that's why I want to do this problem with you. So we have volume equals, well, we've got N. Now let's think about this for a second. Let's think about R. Okay, before we go any further, I'm going to show you a way that I like to handle this because I find that it's for people who are first doing this, it helps really get a mental image on how to do the math. But I've noticed that in the past, when I haven't done it this way, it's been more challenging for people who are first learning this. So let me show you a trick on how I like to, not a trick, but just how I like to use R in this. So if you think about this, this is N times R times T. You can put those in whatever order you want. It really doesn't matter, right? It doesn't matter whatsoever. I mean, you could think about this as N over P times R times T, right? I mean, there's multiple ways to think about this. So what I like to do to handle R, because if you think about it, R it's a variable that has a fraction as a unit. This is a derived unit. And there's 4 variables there. So what you would be doing is you'd be putting a fraction on top inside of a fraction. You'd put a fraction in the numerator of a fractional relationship. So this is what I like to do. I like to change this to where it's N times T over P, and then what I do is I just sort of tease this out, right, and times R. Kind of put that off to the side, and you're going to see here in a second why this is so important, right? You're going to see this in just a second. So now we have volume equals, well, N is 0.250 moles, right? So that's 0.250 moles times temperature. Temperature, we've got 295.78. So that's 295.78. That's Kelvin. All right. All over P. And the pressure was 1 atmosphere. All right. Times R. So R is 0.0821 atmosphere liters per mole Kelvin. And so now I'm hoping you can see why I did this. We have this fraction times this fraction. So now notice all of this is the numerator and all of this is the denominator. Every bit of it is now. So essentially all we've done is this just really extends that. It's all one big fraction. All right? So now let's think about it. We've got atmosphere on top, atmosphere on bottom. That unit's gone. Moles on top, moles on bottom. That unit's gone. Kelvin on top, Kelvin on bottom. It's gone. The only thing left is that unit, which is the unit for volume, and that's what we want. So looking at this, we now realize that this is going to work because the only unit we have left is the unit for volume. So let's just plug everything in. So all right, across the top. So essentially our denominator is a 1, so we just have to multiply everything across the top and we'll have our answer, right? So we got 0.25 times 295.78 times 0.0821, and we see we get 6.0708, right? So we've got 6.07088. There's some other numbers there, and the only unit left is liters. And so let's think about this. We've got 0.250 moles. We've got 22.78 Celsius. So the question is 3, 4 significant digits. If we look at our R value, it's 3 significant digits. So we could look at this and we can evaluate this to 1, 2, 3. That 0 is right there. If we were to go to 4, we'd go to here, but 3 is good. So 6.07 liters. That's our answer. So 6.07 liters, that's a fairly large volume of gas. So we might be starting, at the very beginning of industry processes right here. And in lab, you won't be making 6 liters of gas. If we make 6 liters of gas in class, that could result in some issues. It's some safety issues. So, and the labs that we will do in class will be on a much smaller scale, but the math is still the same. We'll deal with volumes where we'll work with moles of substances in a way that will produce basically milliliters of gas. We still calculate liters, but then we would convert the liters to milliliters. Okay. So hopefully this problem here help. You should see that it's pretty straightforward. Again, list out all your variables. Rearrange your equation to solve for what's missing. In this case, I just have a new volume, but I could have picked anything to solve for. And I'll do some other videos where we solve for, what should the temperature be, or how much pressure will be exerted by the gas under these conditions, etc., etc., etc. Okay. I'll do all those types of things. Or how many moles of gas would we need, or how many moles of the substance would we need, right? Rearrange the equation to solve for your missing variable, and then this isn't a trick, it's a handy way of trying to process this right here, this equation, when you know that one of these variables has a fractional unit. It's just a less messy way to handle that. Otherwise, you just have to get into dividing this out, multiplying by reciprocals, etc., 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 and why do all that extra stuff when we can just tease it out real quick? I basically just sort of factored it out, put it right there to the side, and we're good to go. All right, hope that helped. We'll come back soon and we'll do some more stuff with ideal gas laws with different calculations. Good luck.